Good evening, everyone. Am I audible? Okay. So, welcome to this course, Week 5 discussion. The course is Solar Photovoltaic Fundamentals, Technology and Applications, which is being taken by Professor Soumitra from IIT Roorkee. And I am Ravi Kumar, a PMRF research scholar at IIT Bombay. So, this is discussion about the Week 5. So, in the Week 4, we have discussed about the DSSC solar cell, that is dye sensitized solar cell. And in this week, we will be discussing about the organic solar cells. So this is the same thing, first generation, second generation. In the first generation, we have seen crystalline silicon cells. In the second generation, it was thin film. And from the third generation, we have seen DSSC in the last week. And this week, we are going to start this organic solar cells. And this quantum dots we also covered in the last week as well. So everywhere, one thing is common. There is something, there is some difference in energy at which the generation of electron take place. So in case of crystalline or thin film solar cell, we have valence band and conduction band. But in other things like in DSSC dye sensitized solar cell, we have that dye which generates electron. And same thing we will see what is the reason for generation of these electrons and hole pairs in organic solar cells. So organic solar cell, what is in first, let's see a crystalline silicon solar cell. We will just compare the same thing. So in the crystalline silicon, we have like N-type semiconductor. We have P-type semiconductor. And here we have a junction. So as the light fall on the surface of solar cell, there is electron and hole. So these electrons are collected by this metal grid. This electron moves to this metal grid and this photon move to second metal grid. This is our hole. This is our electron. So one thing is common everywhere. We need some kind of mechanism where we can have electron hole pair. And then second thing comes the collection of the charge carriers. So here like this, these are the metal contact which are used to collect these charge carriers. So this is all about the crystalline silicon solar cell. Here we have semiconductor based inorganic semiconductor. So semiconductor are the two types like organic and inorganic. Today we will see the organic types of semiconductors. So this is the picture of this organic solar cell. So in place of this N-type and P-type semiconductor, we have donor layer and we have acceptor layer. So these are the two different type of organic substance. Like here P3HT is a donor type like substance and PCBM is the acceptor. It means it will give electron while there is some light will fall on the surface of this type of substance, and this substance will accept those electrons. So it is an acceptor and that is a donor. So what happen in an organic solar cell, as light fall on the surface of solar cell, this donor layer and acceptor layer comes into picture. Like Donor layer will give an electron and it will be collected by this acceptor layer. And then there are two electrodes to collect the charge carriers to connect the load. So these anode or cathode will be collected. So like electron will go this side and hole will go upside. So this is the basic working of organic solar cell. But we have seen only one thing, that is there is a difference in the material. Rather than n type, p type, we are having donor layer and acceptor layer. But one thing is missing here. Like in n type and p type semiconductor, we have valence band and conduction band. And if light falls on here, then the electrons raise its energy and it go to from valence band to conduction band, and from this conduction band it is get collected. But there is no valence band, there is no conduction band. So we will see what is the photophysics of these type of solar cells. Any doubt here? No. Okay. So rather than p type and n type semiconductor, we have acceptor layer and donor layer. Other than that, everything is same. So now we will see how a donor level generate electrons. So here you can see this blue color everywhere, it is a donor layer, and this red one is acceptor layer. And in the organic substance, rather than valence band and conduction band, we have this lower part and this upper part. Anyone know? LUMO, HOMO? Which one is HOMO? Which one is LUMO?
Lower one is Lumo.
Lower one is LUMO.
Yes.
Okay. So you are saying it is LUMO and then it is HOMO. Is it correct?
Yes.
So LUMO is the, Vinod said LUMO is valence band. Yes, this is our, what is this valence band, and this is our conduction. So what happens here? Anyone writing something? No. So what happens here? As a photon strike on the surface of this donor layer, now I think it is not right. Yes, it is not right. What I was doubting, say it is LUMO because it says, and it is HOMO. Vinod, you are also wrong because it says least unoccupied molecular orbit, and this says highest occupied. In the valence band and conduction band, we have, valence band is filled with charge carriers, but there is no charge carriers in the conduction band. So same thing is here, like in the above layer there should be no electron or no charge carriers, so that is known as unoccupied. And for the like lower one, it is, as compared to valence band, it is the highest occupied molecular orbit. So what happens, let's come to the point. What happens when a photon strike on the surface of which layer? Donor layer. The charge carriers from this HOMO to LUMO goes up. Why? Because it is absorbing some energy from the photon. So by absorbing this energy, it goes to up, but there is some distance which need to travel. So second thing is diffusion, because there is some distance between this donor and acceptor layer. So this electron need to go to this place. So there will be second step will be diffusion. It is written excitons here because electron and hole pair is known as excitons, and they are binded in case of this organic solar cell. They are referred as exciton. So first is exciton generation, second is exciton diffusion. So diffusion means the traveling of this electron and hole from this like generating side to the edge, means where the acceptor will accept this. This is the second step, that is exciton diffusion. So same here, it is represented like this. And third thing is exciton dissociation. Dissociation, why? What is the like English meaning of dissociation? It is just like a breaking. So what happens in organic solar cell? These electron and hole are binded. They are not free electrons. So that's why we need some energy to dissociate this bond. And the third step is the same one. So at this third step, this electron hole pair get dissociated. And after the dissociation, this electron goes to this acceptor layer, and from this acceptor layer it is collected by metal contact. And on the other hand, this hole goes to this hole remain in the donor layer, and it is being accepted by or being collected by other electron. So these are the four crucial steps for an organic solar cell. Any doubt here? No. Okay. So this is all about the photophysics. So now we have seen like how electron and hole pair are generating here, how they are being collected as compared to crystalline silicon solar cell. So one thing is clear, like what is the working or how is the working of organic solar cell. Next, the dissociation. There are different types of dissociation. We will see one by one. Can someone write here what are the types of dissociation? Have you gone through the lectures? Yes or no? No. Okay. Okay. So let me tell you. Dissociation means it is going, yes. Yes, we know it is energy transfer and charge transfer. So there is a difference between energy transfer and charge transfer. We will see what is that difference. See, the first one is I was saying from donor to acceptor. It need to transfer. So first thing is that from higher level to lower level, this electron go this way. So that is the charge transfer only. So this mechanism is known as charge transfer. But what happens when there is one level is this way and another level this way, and charge carriers from these two need to move this one. So can a charge move automatically without taking any energy from this energy level to this level? No. A charge cannot move from lower energy level to higher energy level without using any energy. If it is possible, then the solar cell will be an automatic device. No, it is not possible. That's why when there is a case for acceptor and donor substances, the HOMO or LUMO are this way. So in this condition, for this HOMO thing, we need to provide some energy to transfer the charge carriers. So that is known as energy transfer charge carriers. It is just about the mechanism. Next, we have how many types of solar cell. We have seen like there is a metal, there is something inside. And we said that is acceptor and donor, or sometimes we say it is active layer. So this is the main layer where the generation of charge carriers take place. So based on the configuration with this layer, we have three types of organic solar cells. Even more are coming, and these three types are like Schottky junction means single junction. Then we have bilayer, and then we have bulk heterojunction. So here only one layer only, and here there are so many layers. But you will understand why it is so. See, the diffusion length. First, I'll tell you what is diffusion length. Let's say there are two places. One is one here and one is here. It is a generating site where this electron is being generated, and this is the collection site which need to be collected. Let's say this is x distance. If our electron started from here and it goes to this collection site, so the condition what we want. But what happens sometimes, due to this diffusion length, if the diffusion length of this electron is very less, so what will happen, this will reach till here only, and till and at this site there will be some hole that will recombine with this. So there will be a loss of charge carriers due to this diffusion length. So see, in this condition, like this is bilayer organic solar cell, if any charge is being generated here and it is collected by the cathode, but the light incident on the surface of solar cell need to be absorbed. If we need to absorb more light, then the thickness should be more. And if we are increasing the thickness, means we are increasing this x, so some charge carrier will be lost because low diffusion length. So that's why there is a bulk heterojunction solar cell. Here these are the blended together, all the acceptor and donor. So the impact of this low diffusion length is minimized here. That's why, because our ultimate goal is to collect large number of charge carriers which are being generated due to sunlight. Any doubt here? And these acceptor and donor are the things only to collect charge carriers. Okay, we will move next. Yes, this is the things which will explain this more clearly. So this is all about the bulk heterojunction organic solar cell. My network is right now. Am I audible right? Yes, okay. So what happened in case of bulk heterojunction organic solar cell? See, this is our donor and this colored one is acceptor. And by making this bulk heterojunction solar cell, what we are doing, we are making sure all the charge carriers that are being generated are collected efficiently. So let's see one picture here. These are the charge carriers being generated, and because acceptor and donor layer are close to each other, and that's why it is simple to collect charge carriers, because these charge carriers are no need to move large distances. So we are minimizing the recombinations due to low diffusion length. So this is all about organic solar cells. And in the upcoming technology, what we are doing, we are just making sure large number of charge carriers are being generated. Large, I'll tell you. There are four things, like first is generation of charge carriers. Second thing is diffusion. Diffusion from donor to acceptor. Third thing is dissociation. It is donor to donor, and here it is donor to acceptor. And fourth thing is collection of charge carriers. So to have maximum efficiency, we need to maximize this. It is like efficiency 1, efficiency 2, efficiency 3, efficiency 4, and overall efficiency is the product of all, 1 into 2 into 3 into 4. So let's assume a case. Here we got 100% efficiency, and here we got 100% efficiency, here we got 100% efficiency. But in case of the charge collection, due to something, we have 0% efficiency. So overall efficiency will be 0. So it is better, rather than like it should be optimally obtained, it's something like that, this efficiency is maximized. So these are the, so we are using different materials to have more diffusion length, to have more dissociation, to have large collection of charge carriers, and to have to generate large number of charge carriers. So it depends on this absorption of sunlight. Any doubt here? So all the research in case of these solar cells are being targeted on the active layer, because active layer is related to this diffusion, dissociation, and generation. This collection of charge carriers is an easy as compared to other these three tasks. So we are using different materials, combination of different materials to obtain the high efficiency. So this is all about these organic solar cells. Now we will solve some questions. If you have any doubt, you can ask here, or we will solve some questions right away. So do we proceed? Okay. So first question says, charge carrier in organic semiconductors are called, and these are the options. Is it polarons, magnons, protons, trions? It means nobody have watched the lectures. Polarons, yes, Vinod. Vinod, yes, Vinod, it is polarons. Yes, polarons are the charge carriers in organic semiconductor. So A is the answer here. Let's move to the next question, which says property of peroxide materials are, and these are the options. Even if you don't know this peroxide material or anything about this, and if you just heard about this from the newspaper or from the daily life, then you can answer this question. Why peroxide is so famous? We will see this peroxide material or peroxide type solar cell in the next class. Vinod said high moisture stability. Deepsika said tunable band gap. If you are saying B and A, then I should go with C, both A and B. Others, just think on the spot. Like it is not like that you need to know this. See, if we are moving from one material to another material, there are some thing in the new material. So if we are moving from crystalline and we are focusing on peroxide materials for the solar cell, so there should be something. And high moisture stability, crystalline silicon is already stable. Then why we need peroxide material? We are not moving for the high moisture stability. Even this is the limitation of peroxide material. They are not stable. Yes, Deepsika, it is right. Tunable band gap. So in case of crystalline silicon solar cell, the band gap is fixed. And if band gap is fixed, what is the limitation? Just think out of the box. It's like we have Eg, then it can only absorb light which have Hc by lambda more than Eg. What if we can tune this Eg? Then we can absorb more and more sunlight. So in order to get large number of charge carriers generated from the sunlight or solar light, we need to have an band gap which can generate charge carriers in every possible spectrum range, and that is possible due to only tunable band gap. I hope you got this. Yes, yes, it is tunable band gap. Band gap is the basic thing which decide how much light you can use in the generation. We will solve some numerical in the last. Some needs only one numerical, but you will understand this thing. So next question, it says bound states of electron holes are collectively called, and these are the options which I repeated in the starting of this lecture. Yes, yes, see. Kushwa, Chandan, Kushwa, Subhraj, Deepshika, it is C. Yes. Excitons. It is a combination of electron and hole that is known as excitons. Why we are saying excitons? There is a reason. In case of inorganic semiconductor, these electrons are free to move. But in case of organic semiconductor, these are loose bound with hole. So we need some energy to dissociate this bond. And that is why this combination or this couple is known as excitons. So C is the answer here. Next question says, which excitons are localized excitons? These are the options. I don't expect you to know this if you haven't gone through the lectures, because it is very specific question. B. B is the wrong answer. C is not the answer. Then A is the answer. So these are Frankel excitons. This is the name of scientist only. So next question says, peroxide materials are discovered by. This is also a factual question. It is not Albert Einstein. It is not Tesla. Then who it is? B. Gustav Rose. Yes. Yes, Vinod, you are right. It's Gustav Rose. Answer is B here. Let's move to the next question, which says, which among the following is a donor material? Donor material. Just remember the second slide of this presentation in the organic solar cell. These are the options. I am talking about donor. Vinod said yes. Vinod said A. Yes. So everyone knows it is A. Yes, Chandan, you are also right. It is A. A is the answer here. Next question, which you gave the wrong answer in the first instance. Let's see. Now you have like understood this or not. It says HOMO and LUMO in organic solar cells is equivalent to inorganic semiconductors. These are the options. Deepsika said HOMO VB and LUMO CB. Okay. Chandan is also supporting the same thing. Vinod also supporting the same thing. B. See, there is nothing to like confusion, nothing to confuse here. I'll tell you simple thing. You are right. Don't worry, Deepsika, Chandan, Vinod, you are all are right. I'm telling you one thing. For the semiconductor, we know it is valence band, it is conduction band. There is no charge carriers. It is an empty state. There are large number of charge carriers. It is in the valence band. So same thing. It should there should be some word in occupied. There should some word in unoccupied. And this should be the lowest, because from highest level, because as you know, in the valence band there are multiple levels. So from this upper level, this should go to this lower level, right? So same thing here, it should be the lowest and it should be the highest. So it is clear, lowest unoccupied molecular orbit. Here highest occupied molecular orbit. LUMO, HOMO. So you got this or do you want me to repeat? Just let me know. But there is nothing to remember, just understanding. Highest to lowest, occupied to unoccupied. That's all. So answer is B, valence band and conduction band. Let's move. Next question. B is the answer here, which says the hole and electron mobilities in crystalline organic semiconductors as compared to silicon is. And these are the options. I told you while I was discussing about the diffusion length. Diffusion length or mobility are interconnected. Yes. If mobility will be high, it will move to the larger distance. If mobility will be low, it will be moved to the lower distance. So if diffusion length is lower, then the mobility should be lower. Yes, Deepsika, it is right, B. Vinod also gave the answer. I think yes, it is B. It is much lower. Okay, let's move to the next question, which says B is the right answer here. Factors affecting the morphology of an organic solar cell are, and these are the options. Morphology comes into the picture when we talk about this active layer. We know this smart here, he said E, all of the above. Yes, it is E. It is donor acceptor composition, solvents, solvent additives, post treatment. So it's all about the fabrication. Yes, all of the above. Answer is E here. Next question. We have the bulk heterojunction in organic solar cells. Just understand it. Bulk heterojunction in organic solar cells, which increases the donor acceptor interface area and allow each of them to be thinner around the junction, is useful for. So it is talking about this thing. Some kind of picture like it is donor, it is acceptor. It is saying all this is useful for what? And these are the options. For the efficient dissociation of excitons generated near the junction, for recombination of excitons, behaves as the source of radiative recombination, or none of the above. Vinod said A. Maristafi Subbaraj also said A. So A is the answer here. Even I'll tell you, this recombination is the poison for the solar cell. Deepsika, yes, it is A. Whenever there is a recombination in a solar cell, it is lowering our efficiency. So it is a poison for a solar cell. So this can't be an answer. This can't be an answer, because why we are increasing the poison in a solar cell? That's why A, B, and C can't be an answer, and D is not the answer. So A is the answer. Even I told you while I was discussing about this thing, like it is donor, it is acceptor. If these are like near to each other, then what will happen? This will jump into this, or this jumping is known as dissociation. So it is like a dissociation of excitons. And answer is A here. And next one is a numerical which you need to solve this right away. It says, what is the theoretical efficiency of a photocell with 2.5 electron band gap when exposed to 100 watt meter square solar radiation through a filter having the following transmittance characteristics: pass without attenuation of all wavelength between 600 to 1000 nanometer and reject all else. And these are the options. Read it, understand it. If you have any doubt, ask. If you need any formula, any constant value, let me know. Even you can Google it, not the question, Google the constant values. Okay, for the simplicity, I'll tell you one thing. What question says? It says, if this is sun and there are radiations and we are having a filter like this, and all the radiations coming from this field is 600 to 1000 nanometer range, and then we have a solar cell here. This is a solar cell, and these radiations are coming on the surface of solar cell. The band gap here is 2.5 electron volt, and this radiation insolation is 100 watt per meter square, and you need to tell me the efficiency, eta. If you want to ask anything, ask in the chat box. formula, please. Okay. What formula you need? Can you identify? How to calculate VOC? Okay. Deepsika, we don't need to calculate VOC here. Because if you are asking VOC, then you will ask me the formula for the, then you will ask me the area of photocell as well. Okay, for the simplicity, I just want to say one thing. Eta equals to fill factor into VOC into ISC divided by insolation into area. And this formula is not needed here. No need. Can you think of what all other things are given here? Okay, what is the basic principle of solar cell? Just I told you multiple times, even like while discussing one problem on the band gap, tunable band gap, then I'll tell you, I just told you one thing related to this easy. Just think about the basic principle of solar cell. Why electrons are going from valence to conduction band, HOMO to LUMO? Why? And that is the thing we need here. Why we are using peroxide material? To generate max photocurrent. Okay. So how will you calculate the photocurrent? What is the constituent of photocurrent? It is electron. Yes or no? And let's assume quantum efficiency of electron, like quantum efficiency is 100%. Let's assume. So number of electron will be equal to number of photon. So can you calculate number of photon here? Okay, first step I'll tell you. What is the range of light which is coming on the surface of solar cell? Let's solve together. Write in the chat box whatever I'm asking. 300 to 700. Deepsika, 600 to 1000. Yes, we know. Nanometer. Then what is the range of? It is not visible range. Yeah, 300 to 700 is the visible one. Yes. Yes, Pulkit. E equals to hc by lambda. So for this range of nanometer wavelength, calculate the energy range. Just convert it nanometer into electron volt energy and let me know the answer. Lambda, we know lambda value is given 600 nanometer. Yashu, I'm saying in electron volt. Whenever you are writing anything on the screen, just write the unit as well. It is in joule, I guess. So just convert it into electron volt. And this 5.2 energies correspond to which wavelength? 600 or 1000? I don't know. Give me this. Like if this is 600 to 1000 nanometer, give me this. Something here, dash something here, electron volt. Give me this. 4000, 1.24 electron volt, and for 600, so 1.65 electron volt correspond to what? Is it for 1000, for 600? 750. Where is 750? We don't need wave electron volt for 750. We need only for 600 and 1000. See, I'm saying this thing. This is already here 600 to 1000 nanometer. I need this one. Give me this. Like Deepsika said, 1.24 for 1000. What about 600? 2.06. Okay, so we got this range. I hope everyone got it. If you are calculating, I can like wait for you. Just confirm me. For 600 it is 2.06 electron volt, and for 1000 it is 1.24 electron volt. I have taken from screen only, I haven't calculated. This range is correct? Yes, no? Vinod, are you calculating? Deepsika already given her answer. Yashu is calculating, don't know what. Okay, do it. 2.07, 1.24. Yes. So it is almost same 2.06. So we consider this is correct. Yes. Okay. Now just leave every calculation behind and think about the basic principle of solar cell. See, this is our conduction band, this is our valence band, and you are saying energy is coming like this: 1.24 electron volt to 2.06 electron volt, and this band gap is 2.5 electron volt. Will any charge carrier will be generated here? No. Then what will be the efficiency? Yes, be zero. So that's the catch. Rather than just focusing on the formula, think on the concept. So blindly don't follow any formula. Think about the thing, what is the it is saying, why it is saying. Yes, it is 0%. So it doesn't matter it is 1000 or 100 or 200 or 500. Until unless the range of wavelength is not correct, there will be no energy generation or energy or charge carrier generation. Even this come to the near IR range. So for this organic solar cell, we have that's it all, and B is the correct answer here. And we are done for today. We will see peroxide and other materials in the next class. I hope you got this. If anyone is having any difficulty in the next last numerical, they can ask. I can repeat it again. You are welcome. Okay, I'll tell you about this. First, I'll tell you here. See, we have two material. Let's say this is an donor and in the periphery we have acceptor. And if light is striking on the donor surface, so there will be electron and hole pair. And this, if this is, there is some material, it's like metal here and metal here, so this hole will go to this way and electron will go to this way. So this is the crude way to understand what is happening. Now we will come to this photophysics. So for this donor and acceptor, we have HOMO and LUMO. It is LUMO and it is HOMO for the donor one. And for the acceptor one, let's say it will be some here only. It's like here. So it is for acceptor and it is for donor. So first case, I'll tell you first thing, then second, then third, then fourth. So first case, what will happen if there will be some light, photon is coming, it will generate an electron hole pair. Here electron, here hole. So it is just in generation. We will write generation. Ask me if you have any doubt in particular case. I hope generation is clear. Okay. For the second thing, it is like LUMO, HOMO, and it is here LUMO, HOMO. So first one is for donor, second one is for acceptor. This charge carrier is generated here, it will move to this position. Same like hole will move to this position. So this is just a movement. Movement is known as diffusion. They are moving from one place to another, that is known as diffusion. So second step is the diffusion of charge carrier. Got it? Okay. So in the third case, if charge carriers at the periphery, oh, it's okay. For the third case, if charge carriers are at the periphery here, so they will be accepted by acceptor. So it's like hole will go this way, electron will go this way. So this electron is being accepted by acceptor. So this is known as dissociation. Got it? This is the third step. First generation, second diffusion, third dissociation. Fourth one left, fourth one is the collection. So for the fourth one, collection means HOMO, LUMO, HOMO, LUMO. So now electron is here and hole is here. We have like metal contact here. Let's say here we have another metal contact here. So they are connected to the external circuit. So it will be collected by this metal contact. It will be collected by this metal contact. This is the fourth step, that is the collection. This is all about the photophysics of organic solar cell. I hope you understood all the four steps. Okay, you are welcome. Can you explain tolerance factor? Tolerance factor, it is about the peroxide, right? Dipsika, it is related to peroxide, right? Yes. So we will see some question as well as the peroxide cells in the next class, next week. It is only related to structure only. Yes. You are welcome, Dipsika. So we are done with the class. If you have any doubt, you want some concept to explain me once again, you can ask it. Otherwise, you are free to leave. Have a nice day.